So to wrap things up from the perspective of Coco values, we learned a couple things. We learned that they're efficiently computable because we can do it with a simple maximization and a linear program added together. What we end up getting is a behavior that's utility maximizing for the two players, and then they split it up afterwards. You can think of it as actually decomposing a game into a sum of two games, one of which is purely cooperative and one is just purely competitive. We're just kind of shifting around the utilities, but we do it in a way that leaves us with two really nice games to work with. The result of that is unique. There is a unique Coco value for each of the players. It's unlike a Nash where there can be multiple different possible values depending on which Nash you pick. There's just the one Coco value. It's very convenient.
That is convenient because that means there's an answer.
There is an answer, yeah. We've discovered that, in fact, you can generalize this notion not just to matrix games like we talked about, but actually to stochastic games in general. And we get an algorithm that we call Coco Q. Coco Q is a Q-learning-like algorithm that uses Coco values to learn a strategy in a stochastic game where they actually can make little side payments after each move. So the two players move, and then they divvy some stuff up, and then they move again, and they divvy some stuff up. And those side payments actually end up being sensitive to issues like we just got really unlucky, or I'm about to take an action which is very risky. And so, you're going to have to pay me to take that action. And the payments have these nice interpretations in terms of kind of paying people for taking risky actions and giving them the benefits of things. It's neat because this actually converges, this Q-learning algorithm converges, in spite of the fact that the operator, the Coco operator, is not a non-expansion. We've talked about non-expansions in the context of generalized Q-learning. This is a case where that analysis actually fails, but there's a different analysis that you can use to show that the algorithm actually converges. So that was surprising to me anyway. I spent a lot of time worrying about non-expansions, thinking that they were the answer to everything.
Yeah, they answer to everything except for things that are
just not this thing.
Yeah, cuckoo for Cocoa Puffs.
One thing that's worth pointing out is that what you get at the end of this is not necessarily an equilibrium, which is to say, once we've computed what the Coco values are, I might not want to play that game. I might not want to do the side payment. I would rather get my value in a Nash equilibrium or something like that. And so that means that to really make this work, this side payment mechanism has to be binding. They have to agree in advance that whatever happens, we're going to do what the Coco value says we should do. And it's somewhat beneficial, but making this binding agreement in general is not beneficial. It could be, for some players, they'd rather just not do it. So it's not an equilibrium in the same sense as like Nash and correlated.
So we're going to have to hire police officers.
We're going to have to hire police officers to divvy up our bananas.
Okay, so just like real life.
So thank you for letting me have a chance to come and discuss Coco values, which otherwise we would have not gotten to.
But I like this. So should I learn from this that basically we should always be doing Coco values or Coco? Yeah, we should always be doing Coco and, hiring police officers, make things binding?
Boy, I don't know. I mean, in general, you tend to get a higher sum of values from the Coco values, so paying the police officers probably makes sense. So it might be worth hiring them. For specific games, it's not necessarily true. It doesn't necessarily kind of fit. Another problem with the notion of Coco values is that it doesn't really generalize if you've got more than two players. So this is specific to the two-player setting. If you have three players, you can't split it into, three matrices, one of which is cooperative, and another which is competitive, and the other which is, combustible.
Well, what if you did all pairwise games? You'd have to get extremely lucky.
It doesn't seem like there's a natural extension of this that works for more than two players. I mean, it's an open problem, and so no one's shown that you can't do it. So, that could be a homework problem.
Oh, yeah, that's cool. And then anyone who gets PhDs for everyone.
PhDs for everyone. Wouldn't that be nice?
That would be nice. Okay, so we've gotten through Coco values. It's good. So we worked together, and now we've done two solution concepts in some detail.
Yeah.
Everybody wins.
That's the thing. And now we can actually do side payments to kind of divvy up afterwards.
So what are you going to give me?
I am going to give you back the pen so that you can wrap up the section 3 on game theory.
Sounds good.